Next step is I want to get a 1/2 in there. Since I'm so close to having kinetic energy here, I'm going to put an extra 1/2 in here. So if I'm multiplying by 1/2, I have to also multiply by 2 in order to keep it balanced. So this becomes 2/3 N over V times 1/2 M V squared. And this V right here is the volume.
So why are we multiplying by 1/2?
I'm multiplying by 1/2 and by 2 just to cancel them out. Because I want that. That's the average kinetic energy. Because I'm starting out with all the masses are the same with mass M, 1/2 is the constant also, regardless of the problem. Unless the mathematicians have come up with the best with our heads. So I got the average kinetic energy circled in black right there. So now let's finish it up. You're so close. I'm going to clear this. So I have this average pressure here is equal to 2/3 N over V times my average kinetic energy. That's a capital K. I'm going to multiply both sides by the volume. So I got PV is equal to 2/3 in K.
Oh, I thought we were like doing the ideal gas.
Yes.
Wait, are we?
And what does PV equal?
NRT? Yeah.
For you chemists. Or if for the physicist.
I like the ideal gas.
This is the ideal gas law that I was taught also because I took chemistry first. This is one source worded it as this is the chemistry version and this is the physics version. They're the same thing. This N right here is the number of moles. This capital N is the number of particles. This is the ideal gas constant.
Yeah. It's like
And this is Boltzmann's constant.
is it like 0.0821 or something?
I always have to look it up.
I think that's what it is.
And by the number of gas particles is usually like some number like 6.24 times 10 to the 23.
Oh, Avogadro's number. So the number, you take the number of particles, divide by Avogadro's number, you have the number of moles.
That's what I'm thinking.
6.02 times 10 to the 23rd. That's the number of objects in a mole.
And T is just temperature
And capital G is temperature, yes, in Kelvin.
in Kelvin, okay.
So you have to like add like 290.
All right, so I've got this equal to that. The number of particles doesn't matter, that goes away. And so if I'm solving for the kinetic energy, or average kinetic energy, that's going to be equal to 3/2 times Boltzmann's constant times the temperature. And we now have a relationship between average kinetic energy and temperature. So as the kinetic energy in an object, the average, as the temperature increases, the particles have to be moving faster on average.
Yeah. That's like, yeah, that makes sense.
Wait. What is the K8?
That?
Yes.
That's a B.
Oh.
What?
Yeah. So as temperature increases, pressure increases.
That K sub B is Boltzmann's constant,
Oh, okay.
which I suppose I wrote down somewhere. It's not one of those constants that I use regularly, so you just look it up. Questions?
Will this content be for the test on Wednesday?
Let me address that in a moment. Questions concerning the physics of it, not the grade of it.
But I'm glad you came. I don't know where we're going with it. I'm satisfied.
Okay, Hector's satisfied, so we can stop there with that.
Is Boltzmann number, or Boltzmann's constant the same as like the 0.0821, the ideal gas
No,
constant?
it would be, the relationship is that NR is equal to big N KB. I know that, number of particles divided by Avogadro's number is equal to little n.
Yeah.
So R over Avogadro's number is equal to Boltzmann's constant.
Oh. So they're not.
Like I say, so you can put that in, big N's cancel, left with that, so that's the relationship there.
Okay. So
This is 800 something in SI units, I forget what the number is again, I don't use this that often. This is 6.02.
Yeah.
The capital N is number of particles.
Yes.
So it's
Moles was one of those things that when I took chemistry, I just found it confusing. And at some point it clicked and I finally realized how to deal with it.
Yeah, that was.
But if you haven't, the thing that finally helped me with it is just a number, like a dozen. I've asked problems with moles on it before and gotten confused looks from students. And then I changed it. I got rid of moles and I did the problem in terms of dozens and they could get it. And then I throw the word mole back in there and suddenly there's this disconnect.
Wait, you taught chemistry?
I've done tutoring for all sorts of subjects. And for one unfortunate student, I did one session of tutoring Spanish.
Oh.
That was a mistake, which they realized quickly and they got someone who actually knew Spanish.
Hey, glad they figured it out.
I would love to know what your Spanish tutoring was like.
I'm trying to remember how to pronounce the letters. I mean, it was at elementary level, it was just doing vocabulary, but my pronunciation was probably far from competent. Okay. I wanted to at least get that down. There are a couple of things I could go over, but there was a request to do a problem of each.
Yeah, like one from mass energy, one from, I guess,
Work energy, I think you mean.
yeah, work and energy.
So this was pandemic test. Man,
Pandemic test, tough.
you know, go into it with the illusion that all the stuff's there. They get all this stuff on their own. They don't need the face-to-face.
That works out, right?
Yeah.
Definitely.
They overestimated.
Was it 16
Alright.
weeks back then? Is it 8? Was this class 16?
They were all 16. This is the first time I've done 251 in 8 weeks.
We got
This is the first one?
We got got.
You got
We got
The first time I've done.
We really got
Wait,
unlucky.
this is the first.
This is the first one? No
The
wonder.
test dummies.
We are the dummies.
So there was, Ms. Sasson did a 251 the first 8 weeks, I think.
That's awesome.
Sasson,
I thought it was
Sasson. It's spelled Sasson, but it's pronounced Sasson.
Oh, okay, Miss Sauce.
Yes.
I thought it was.
We could also fit in, I don't know if this relates to Zach's question, but I have a few master spec questions for 11 and 12. So if they happen to coincide with the content he's asking for, does that make any sense?
Or, when since master set questions are test problems, or test problems, why don't we do the master sets? And then we'll see what we have covered.
So for chapter, master set 12, I had a question for both 5 and 6.
Alright, I will need to see it, since apparently I left that folder in my office. All right, so 5. Steve was captured, ended up in prison. This was part of a, basically, bad guy, first problem, commits a crime, and then is being chased after that. That was the storyline. So Steve was captured, ended up in prison.
He needed the Lord.
He's in jail.
Yeah.
I guess properly, you don't go to prison until after you've been convicted, so I guess he ended up in jail, so he's already been convicted.
Okay.
Alright, good to know.
Or at least they didn't post bail or something.
What's that?
Or at least they didn't post bail or something. Point is, he's locked up.
I would
It's all
have
that
paid
matters.
his bail.
Anyways.
Time for a walk.
All right, so we've got, Steve drove away from the prison, spare tire, so I give a radius. Getaway car supposed to rotate, so I've got a rotational motion problem. Angular acceleration is modeled. And then magnitude of the total acceleration. At some point, I give an initial, so let me just do numbers that are close. We'll make this 0.5 meters. 3 minus 16 over t plus 5, k hat, inappropriate units, and omega initial 0.2 radians per kilosecond. This is in kiloseconds. And so magnitude of the total acceleration, the point from the edge after 2, so when t is 2 kiloseconds. Now when I say total acceleration, what are the 2 types of acceleration we can be dealing with here?
Like linear and rotational.
Angular.
Rotational or angular, either one works. But how do you add those together to find a total?
Equations of motion.
Isn't it like the square root of?
Yeah, you're going to do a Pythagorean theorem. But if we're doing that, linear or tangential acceleration and angular acceleration are related to each other. What's the other kind? I got something traveling in a circle and that circle is changing its angular velocity.
Centripetal?
Yeah. So after 2 seconds, I'm going to have some tangential acceleration, and I'm going to have, so that's the center there, as it goes around. I'm going to have a centripetal acceleration. What's the relationship between tangential acceleration and angular acceleration?
Angular.
There's a formula.
Yeah.
Tangential acceleration is angular acceleration times the radius.
Yep. So tangential acceleration is just r alpha. Just like v is equal to r omega, and s is equal to r theta. So when t is 2 seconds, I can just plug into my formula here, and I end up with, let's make it 3 seconds, just so that this works out nicely. At 3 seconds, I get 16 over 8, so which is 2, so 3 minus 2, so alpha is 1 radian per second squared. Kilosecond squared, since I just do kiloseconds here. My radius, I changed to 0.5, and so my tangential acceleration is 0.5 meters per second squared.
Not kiloseconds.
For kilosecond squared.
Are kiloseconds real?
It's just 1,000 seconds.
Okay. That's what I was
That's a
thinking.
lot.
But
Typically, I don't see things in kiloseconds, you just do something times 10 to the third seconds, but
That's a lot of time. That's like almost an hour. Wait, yeah.
The other way, right?
a kilosecond's about 20 minutes.
Yeah, so that's like
So
an hour.
3 kiloseconds is an hour, right?
3.6 kiloseconds per hour.
Yeah.
Maybe we should measure
But-
points in kiloseconds.
If 1 kilosecond's 20 minutes, with 3 kiloseconds just be an hour?
3,600 seconds are in an hour.
Oh.
That wouldn't be exact.
It'd be like 1.2 would be 20 minutes, but.
The 3 kiloseconds would be shy of an hour.
5, 6, 7 hours.
5/6 of an hour.
That's fine.
All right.
Got 8, no.
So now we have to figure out the centripetal acceleration. Well, there's 2 formulas there. What are the 2 formulas for centripetal acceleration?
mv squared over
Oh.
r. Wait, v squared over r.
There we go. Or
Oh god. Some with omega.
Yeah.
Omega
Omega r squared?
Omega squared over r? No.
Omega squared r.
there we go.
Damn it.
Omega squared.
I'm so close.
We're all just like yelling out random. It's Omega and r and something squared.
As a group, we can nail this thing.
Say as many possible answers as possible.
So I have to figure out what omega is at 3 kiloseconds. So I've got alpha here, so I can come up with a formula for omega. If this is alpha, how do I find omega?
Take the integral of alpha.
Yeah. So the integral of alpha, dt omega. Oh, what the heck? Throw the vector into it. So we end up with 3t minus 16 times the natural log of t plus 5. Plus some constant. And so now we can, so the whole purpose is giving you the initial angular velocity, so you can figure out what that constant is.
Is that ln next to the 16? Is that an ln next to the 16?
That's
Natural log?
16 natural log.
Okay. That's okay. Just double check.
The typewriter we had when I was growing up, a manual typewriter, there was no 1 on it. If you wanted to write the number, type the number 1, you had to press lowercase l.
What?
Were there other numbers though?
There are, all the other numbers were there, just 1 wasn't there.
Wait. So they had through 2 to 0, like 2, 3, 4, all the way up to 0.
Yep,
But not a 1.
not a 1 because you used the lowercase l for it.
That's crazy.
All right, so let's plug in, I know this is my initial, when I believe the problem says that time is equal to 0. So we plug that into there, so omega of 0 is equal to 0.2, which is 0 minus 16 natural log of 7 plus c. So c is gonna be whatever that is.
Be 8 instead of 7, because it's 3 plus 5 instead of.
Yep, 8. Thank you.
I'm confused.
No, whoa. No. 7 was wrong also, 5.
Oh.
Oh.
I was wondering.
How is why isn't the initial angular velocity not just the constant?
You mean, why is c not equal to that?
Yeah.
The initial is the value at, in this case, when time is equal to 0. Because we've got a natural log in there, it's not like all the terms. If this had been a polynomial, all the non-t terms would have dropped out and we would have just been left with a constant. But in this particular case, because of that natural log, that pesky natural log, it doesn't work that
Okay.
nicely.
Thank you.
And so whatever 16 natural log of 5 is, it's something.
0.8.
What is it?
I don't know. Yes.
All right, so natural log of 5
I got you.
is 1.8.
25.751.
I was a little bit off.
Alright, so we now have omega, a formula for omega as a function of time to be 3t minus 16 natural log of t plus 5 plus 25.751. Don't forget, if the question asks what's the formula for it, don't forget units for the constants. And so I want to know at 3 seconds, so omega, okay. At 3 kiloseconds, this becomes 9 minus 16 natural log of 8 plus 25.751. Okay, that's a 9, not a 0.9. When I turn that to a plus.
Wait, is that, okay, so is that a point or a plus 9?
It was 3 times 3, so it's just plain old 9.
Okay,
There's an accidental
9
straight line.
minus 16 ln of 8 plus 25.751 is 1.4799.
And that's gonna be radians per kilosecond.
Yeah.
And so therefore, our centripetal acceleration is 1.4799 squared times 0.5, which is about 1.12. Somebody's gonna correct me.
Wait.
1.095.
And that's radians per kilosecond squared. And so we've got the pieces now, so the total acceleration is the sum of these two. They are vectors, don't just add them straight up like they're scalars. And so the magnitude of our acceleration is the square root of 0.5 squared plus 1.095.